0.52. And I would say the probability of short hair would be equal to 0.48. And if I pick someone at random, what's the probability that this person is male? 400 out of 1,000, 0.4. And probability that someone is female, if I pick someone at random, 600 out of 1,000, or 0.6. Is that okay? So if hair length and gender are independent, under independence, then the probability of long hair and being male would equal the probability of long hair times the probability of being male. So that would be 0.52 times 0.4, and I would get 0.205. Is that right? 208. Good? Okay. And if I wanted to put in an expected count for the number of males with long hair that we would expect if it was independent, what would I do? I would take this probability and multiply it by 1,000, and my expected count would then be 1,000, the total number of people I observed, times 0.208, and I would expect 208 people to have long hair, to be males with long hair. So we would do that, the same thing, for all 4 cells, for all combinations of the variables or categories. Okay. This 0.52, how did I get 0.52? 0.52 was done by taking 520 divided by 1,000. 0.4 was taken by doing 400 divided by 1,000. And then if I multiply, so this would be the probability, and if I multiply that by the total count, I would get my expected number, 208. So the expected count can be found like so. Okay. It's exactly the same thing that I've written here. I'm just writing it as a fraction. Okay. This can all be simplified and into a form that can be used for any cell. And it's that we take the row total, 520, multiply it by the column total. Okay. And we can, if we see that we're dividing by the grand total and multiplying by the grand total, we can see that this count cancels, and so the expected count will always be the row total times the column total divided by the grand total. going to create, so this is my observed data. Let me just create the expected data. So expected, male, female, long hair, short hair. And we did the math and we found the total number of long-haired males to be 208. I can go through the process and find the total number of long-haired females, short-haired males, and short-haired females. Okay. Well, one thing is that we know that the total of males has to be 400. So if I have 208 here, that means I have to have 192 there. And the same goes for the row totals as well. So 208 plus some number has to be 520, so I have to stick in 312. And I would have to stick in, I can't do the math for some reason, 288. Okay? So this illustrates something here. And that as soon as one number was set, the other three numbers had no choice. They were locked in because the rows must add up to their row totals and the columns must add up to their column totals. So when you have a 2x2 grid, you have only 1 degree of freedom in this test. Okay, so there's only 1 degree of freedom. And anytime you are doing a chi-squared test for independence, your degrees of freedom is equal to the number of rows, n rows minus 1, times the number of columns minus 1. So in this case, we have 2 rows and 2 columns. So 2 minus 1 times 2 minus 1 is 1. We have 1 degree of freedom. Alright, and now we can calculate our chi-squared test statistics. So I would do the observed minus the expected squared divided by the expected. So I would do 40 minus 208 squared over 208 plus 480 minus 312 squared over 312 plus, so it gets a little tedious because you have four numbers to calculate. And this number is going to be huge because we're squaring quite a large number. So 168 squared over that. I get a chi-squared statistic of 471. I think. 471.15. I don't know. Maybe I did my math wrong. Before I go on, I just want to make sure this process is okay and if anybody has any questions. Okay. So my chi-squared statistic ends up being this ridiculously large 471.15. So I would go to my table and I would see, okay, that's off the charts. My p-value is definitely less than 0.0001, okay? So I would have an incredibly tiny p-value, whatever it is. So that's saying if hair length and gender are not related, what is the probability that from random chance alone, I happen to see data that looks like this? The probability of seeing something like this is incredibly unlikely. You know, less than 1 in 10,000, or actually, oh, you know what? I messed up here. We did not, what did I say for my alternative? Oh, I just said not independent. Okay. So in this case, I said not independent, so that would be a non-directional test. I could have specified, I could have said, we're expecting to see the probability of long hair given male to be less than the probability of long hair given female. And in that case, I would have a directional alternative. Okay. And then I would have to do my directionality check. And that it would match the directionality. Okay? So, well anyway, if it's non-directional, my p-value is less than 1 in 10,000. And if it was directional, it would be less than 5 in 100,000. So, and actually it's much more smaller than that. Okay. So we would say we have evidence to reject the null and conclude that hair length and gender are related, or are associated. Yes?
So if it's directional, you would divide that tail probability by 2?
Yes, assuming you passed your directionality check. So if you had a directional alternative, basically you would just change this equal sign to a greater than or a less than. And then you would just want to make sure that your data supports that. Okay, so if I said, if the alternative, is it okay if I erase this right here? Oh, I already did. The alternative would be probability of long hair given male is less than the probability of having long hair given female. And so we would go to our table, and to do our directionality check, we just want to verify that if I did, what's the probability, or when we look at our data, and if I pick someone who's male, what's the probability that he has long hair? Okay, according to our data, probability of long hair given male would be what? 40 divided by 400, 0.10. Okay? So this is from our data. And then when we do our data for long hair given female, it would be 480 divided by 600. And I would get 0.8. And so our data does support that 0.1 probability of long hair given male is less than probability of long hair given female. So our data passes our directionality check. And then we would go through the test just like we did. The chi-squared statistic would be calculated the exact same way. None of the numbers change. And it's just that at the end, you would take your p-value and divide by 2. Or, sorry, you would take your tail area and divide by 2 to get your p-value. So, you know, this might involve just looking over some of your notes from chapter 3. Probability. Did I just go out? Okay, I don't know how to. So you might have to look over some of your notes from chapter 3 on probability to just make sure you have this given and independence and those rules figured out. Gabe? Yes?
I don't know if you erased it or if it was, oh yeah, but calculating the expected count.
Yeah. So the expected count, I went through the process of saying under independence, we say the probability of long hair is 52%, probability of male is 0.4, and under independence, the probability of long hair and male would be this times this. And we get a probability of 0.208, and to get the expected count, we would do 1,000, our total number of observations, times that probability. Okay. That was the explanation. But the result, the end result to getting your expected count is just doing the row total times the column total divided by the grand total, which is exactly what we did here. Because to get 0.52, I did row total divided by grand total. And to get 0.4, I did column total divided by grand total. And so to get this, I did essentially doing exactly that. That's all. I think that's all I need to say about that. Yes?
So the expected count is referring to what exactly? The 208? What is
Yeah,
it
the
saying?
208.
Yeah.
So this would be if the null hypothesis were true, meaning if gender and hair, length of hair are independent, how many people would we expect to see that are males with long hair? Okay, we would expect to see 208, because it would be, if 400 people, 40% of your population is male, and 52% of your population have long hair, and there's no relationship with each other, we would expect basically 52% of your 400 males to have long hair. Or, let's say we take handedness, left hand and right hand, okay? There's no connection really between that, as far as we know. So let's say 15% of the overall population is left-handed, okay? If we have a room of 200 people where 100 are male and 100 are female, how many left-handed males would we expect to have? We would expect 15% of that 100 males to be left-handed. We would expect 15 left-handed males, okay? Because we're just multiplying that together. And something like long hair and short hair, we know that it's not independent. We know that there's some kind of connection there. And so when we observe our data, we see that. But if they were independent, this is what we would expect to see. That's what the expected count is. So the expected count is what would we expect to get if the null hypothesis were true? And in our case, the null hypothesis is that the two variables are independent. Yeah.
Does the expected count value factor into our conclusion? Because like in our conclusion, we're really just looking at the p-value.
Mm-hmm.
Does that expected count value play a role?
The p-value is the probability of observing your data, or
Yeah.
something more extreme if the null hypothesis were true. So the expected count itself,
So it's not.
it factors into the idea of something more extreme. So we're seeing only 40 long-haired males. That is different from what we would expect. And so something more extreme would be seeing something fewer than 40 males with long hair. Okay. Are we good? Okay, so then that is it for material covered this week. You have a lab this week. It's different in that you are going to read a research article, okay? And this research article, it's from JAMA, Journal of American Medical Association, and they did it's a couple years old now, or a few years old now, but they did a test to see if St. John's wort could be used as a treatment, alternative treatment for ADHD. Okay, and so they looked at kids with ADHD and gave them different treatments, and they measured to see how effective it was. Okay, it's pretty much they're using confidence intervals and t-tests in their analysis, and so I wanted to give this to you guys so you can see how t-tests and confidence intervals are used in a real-life application. Okay, I have questions for you to answer regarding the article. So do your best with that. So you don't have to deal with R this time. So have a wonderful Thanksgiving week. We won't see you guys next week. We'll see you in 2 weeks. Okay.